Let's calculate some Taylor polynomials. And after we've got the polynomial approximation to our function, we'll use the remainder formula to figure out how good of an approximation we've got. So, function I want to start with is f of x is the sine of x. I'll need to center my polynomial somewhere. Typically, we use the number a for that in the general formula, and my number a will be pi divided by 6. I also need to specify the degree of polynomial I'm interested in. For this example, I'll be looking at the 4th degree Taylor polynomial. And finally, I need to specify an interval. Because the Taylor series converges faster near the central value, I won't be able to figure out my amount of error unless I specify a certain interval that I care about. So I'll be looking at the interval between 0 and pi over 3. The very first thing that I like to do is I like to build a table where I look at my different values of n, and I'm going to switch to hand-drawn for this. I need to calculate the successive derivatives of my function. Remember that the superscript with parentheses is indicating a derivative. I've taken n different derivatives here. And then once I have those derivatives figured out, I actually need to evaluate them. And I'm going to evaluate them at the number pi divided by 6. So to find the coefficients for my Taylor polynomial, I evaluate each of the different derivatives of my function at the center value, pi over 6. Now, to find the coefficients, I'll look at n equals 0, n equals 1, n equals 2, n equals 3, and n equals 4. Those will give me the coefficients that I need to calculate the actual polynomial that I care about. But I am going to go one further. I'm going to go out to n equals 5. And the reason I'm doing that is because I also want to calculate the Taylor remainder. And the Taylor remainder formula requires me to calculate one more derivative than what I need for the coefficients of the polynomial. The error involved is determined by whatever the next higher derivative would have told me. So let's get to work. For n equals 0, I'm taking 0 derivatives of my function, which means that the formula is unchanged, and I'll just have regular sine of x. This is something that's true for all functions, just sort of a quirk of the way that we like to talk about derivatives. The 0th derivative of any function is just the function itself. Now I look at the first derivative of this function, which I know the derivative of the sine function is cosine of x. I'm going to keep filling up this table. The second derivative will be just the derivative of the cosine function, the derivative of the first derivative, and that's going to be minus sine of x. Next, for n equals 3, I'll have the third derivative of the sine function, which is minus the cosine function. And for the fourth derivative, I'll have positive sine of x. So we've probably seen this before, that the derivatives of the sine and cosine functions make this pattern where they alternate between the sine function and the cosine function. There'll be some negatives showing up, but after 4 derivatives, we end up with the function we started with. That's kind of neat. So that's going to mean that my 5th derivative, n equals 5, will again be cosine of x. Now I'm going to evaluate these things. Each of the different derivatives here, I'm going to plug in x equals pi divided by 6. So for sine of x, I'll get 1/2. Pi over 6 is one of those friendlier angles that you can commit to memory. Sine of pi over 6 is always 1/2. Now, cosine of pi over 6 is another value that's worth memorizing. And this is the number that when I square 1/2 and I square this number, I can add them together and get 1, right? That is always true of the sine and cosine functions. So this number here is irrational. I'm writing it with a numerator square root of 3 divided by 2. Now, with these two entries on my table, for the way that this problem is set up, I actually have all the information I need to finish this column, because the rest of my derivatives are just negatives of the functions that I already wrote. So minus sine of x, if x is pi over 6, gives me minus 1/2. Minus cosine of x, if x is pi over 6, I will get minus the square root of 3 over 2. And then I'm back to where I started. So sine of pi over 6 is again 1/2. Cosine of pi over 6 is again square root of 3 divided by 2. I won't actually need this root 3 over 2 for my Taylor series coefficients, right? I am stopping at the 4th power of x to get my degree 4 Taylor polynomial. So, what are the actual terms of my Taylor polynomial? There should be a linear term. Let's not forget the constant term, right? The degree 0. So constant, linear, quadratic, cubic, and quartic, degree 4. And in total, that'll be 5 terms of my Taylor polynomial. So the constant term is going to be 1/2. And I've got to divide by 0 factorial. Since 1/2 is already a fraction, I'm going to write this as 1/2 times the fraction 1 over 0 factorial, just to make things a little tidier. And then I'm going to multiply this quantity by x minus pi over 6, all to the power 0. Now, in the end, this expression here that I've written is just going to reduce down to 1/2. But sometimes I like to put the power 0 there and the divide by 0 factorial, just to make the pattern a little bit more explicit. Let's continue. For the linear term, I'm going to use this number here, root 3 over 2. Now, to get the Taylor coefficient, I need to divide by 1 factorial. That's a little redundant for the constant and for the linear term. 0 factorial is the number 1, and 1 factorial is also the number 1. But here is my linear term then. So that's 2 down, 3 to go. The next number I'm going to use is negative. I'll have minus 1/2. I'll multiply this by the fraction 1 over 2 factorial. And I will multiply that by the power term x minus pi over 6 all squared. So notice that the factorial number corresponds with the exponent here. For my cubic term, I again have a negative coefficient. So I'll write this as minus root 3 over 2. And I need to divide by a factorial number. This time it's the 3rd factorial number, which I know 3 factorial is 6. And then I've got x minus pi over 6 all to the power 3. Now, I wanted the degree 4 Taylor polynomial, so I will add on one last term. I'll have 1/2 from my table. I have to divide by 4 factorial. And then I will multiply by x minus pi over 6, all to the power 4. So what I've written here, this whole thing is the degree 4 Taylor polynomial. I've got it in green there. You need all 5 of those pieces to build up the quartic polynomial. Now you might notice that I have not simplified these coefficients, and I've chosen to leave them written out this way just to help show the pattern involved for calculating a Taylor polynomial. If you really wanted to, you could say, okay, the constant term is 1/2. The linear term has a coefficient of √3 on 2. The quadratic term has a coefficient of -1/4. The cubic term has a coefficient of -3 over 12, excuse me, -√3 over 12. The quartic term has a coefficient of +1 over 48. However, I am not going to expand out these different powers. It's a little bit more practical in this setting to leave those power terms written out as x minus pi over 6 raised to some power. Part of this is because I'm looking at, middle to large values for those exponents. I don't really want to write out the whole expansion of x minus pi over 6 raised to the power 4. And as I take more terms in my Taylor series, it just gets worse from there. The other reason that this is a practical thing to do is that it reminds me that this Taylor polynomial comes from Taylor series centered at pi over 6. So the best approximation I should see from this formula is when x equals pi over 6. This formula will match exactly to the value of the sine function, right? Everything here will go to 0 except the constant term, which we have rigged to display the correct value for our function. So it's just a nice way symbolically to remind ourselves of where this approximation will do its best job, close to the number pi over 6. Okay, but on that note, let's actually measure the error involved for other values of x. And for this, I'm going to use the Taylor remainder formula. So my number 4 remainder is going to correspond to the number 4 Taylor polynomial. But remember that everything in the remainder formula is going to have its number n increased by 1 from where we saw it in the regular Taylor series. So I actually need the 5th derivative of my function, which I thought ahead and I already calculated out what the 5th derivative is going to be. And I need to multiply by x minus pi over 6 to the power 5. That should be a 5, excuse me. And then all divided by 5 factorial. So this is going to be in the numerator. My 5th derivative is the cosine function. And it's going to be evaluated at some number z. And this is a place where the remainder formula is not explicit. All I really know about this mystery number z is that it's some number between x and the center value, pi over 6. So if x is larger than pi over 6, z will be to the right of pi over 6, but to the left of x. If x is to the left of pi over 6, then reverse all that. For this purpose, I only really care about the magnitude of my error, so I'm going to put absolute value bars around everything I see here. I don't really care if the error is too much or too little. I just want to know the size of it. And further, I want an error term that's an explicit number. And the way that I calculate that is by overestimating. For both my z and my x, I'm going to think about what's the worst thing that could happen, right? I'll overestimate my error so that at the end of the day, I can guarantee my error is less than blah, whatever it is. So for the cosine function, I don't actually know what number z is, but I do know that z has to be some number between 0 and pi over 3. Well, I know that the cosine of 0 is 1, and I know that that is the largest the cosine function can get. So the very worst thing that could happen in terms of error is if this cosine of z were exactly equal to 1. That's the biggest that I could see here. I'll keep going with this idea to overestimate and get a fixed number for my error formula. So the way it's written right now, this error formula will give me different amounts of error for different values of x. That makes sense. The Taylor error here does depend on how close my number x is to pi over 6. If x was exactly pi over 6, then my error should be 0, right? I'll have 0 to the power 5 here. But for other values of x, I will see more than 0 error. So this time I'll say, well, I've got x minus pi over 6, and this is all raised to the 5th power. So power functions like this, since 5 is a positive number, the biggest this could be is going to correlate with the biggest input I can give this power function. So for this problem, the biggest that could be is x equals pi over 3. If I choose an x smaller than that, I'll be getting closer to pi over 6, and that will decrease the amount of error. And if I shoot past and go to the left, I'll have a negative number here, but since I'm using absolute values here, it'll just give me whatever I would have for the corresponding positive value. Now, pi over 3 minus pi over 6 is still pi over 6, and I'll be raising that to the 5th power. Now my numerator is just the formula for some number. My denominator was already the formula for some number. The number is 5 factorial. So written out this way, I have a single number that is the worst possible error that my Taylor polynomial could have in it. So as long as x is a number between 0 and pi over 3, I am guaranteed to have this fraction as the worst possible error I could see. Now, what I'm doing on my phone really quick here is I am calculating to find a decimal approximation of this number. So I've taken pi over 6, which is a number slightly bigger than 1/2, and I'm going to raise that to the power 6, and then divide by 5 factorial, which I know 5 factorial is the number 120. So this gives me a decimal approximation for my error term, that the biggest my error could be is, and I'm going to round up on this, the biggest my error could be is 0.0002. It's really 0.00017171589 and so on, but I'm just rounding up to the 4th decimal place. So what this is allowing me to do is I can specify the function that I want. This was a pretty easy one, just sine of x. And I can specify what kind of approximation I want. So for all of these Taylor polynomials, yes, I'm going to end up with a polynomial for my approximation. But the thing that's nice about polynomials is they only involve the simplest mathematical operations. If I want to know the value of a polynomial, all I really need to know how to do is addition and multiplication. And those are two of the very fastest calculations that modern computers are designed to handle. I like to think of this approximation work that I'm trying to build a machine. I've got a lever or a dial on there that I can specify what kind of approximation. For this problem, I decided that I want a quartic approximation, a degree 4 polynomial. So I just set the dial. I tell the machine I want a polynomial of degree 4 to approximate my function. I also have to tell it where to center the approximation, which does the job of saying, okay, where is this approximation going to be the best? This approximation will be dead on for the number pi over 6, and it will be pretty close for numbers close to pi over 6. So here I've got a whole 3 decimal places of accuracy. Maybe that's enough for my purposes. But I wouldn't have known my margin of error without calculating the remainder. I needed to use this formula in order to mathematically establish that my margin of error is, in fact, 0.0002. And again, my margin of error is actually a little bit less than this, but I've rounded up to guarantee that no matter what, this tolerance will be, this tolerance for error will be satisfied by my approximation.